In this video, I will talk about definition of bivariate. Bivariate extreme value. Right? Okay, suppose you have two variables. Okay? So in the previous video, X could be air temperature, right, or sea temperature, Y could be wind speed, right? That's one example, right? Okay. So you have data on X and you have data on Y. Now there are many different ways to define a bivariate extreme value. The most traditional, the most common, definition of a bivariate extreme value is as follows. What you do is you take the largest of the data on X, okay, and you also take the largest of the data on the Y's. Okay, and you call this this is the notation I shall use to denote the bivariate extreme value. So it has two components. The first component, capital M n, 1, denoting the largest of the data on X. The second component, denoted by capital M subscript n, 2, denoting the largest of the data on Y's. But the problem there are drawbacks in every definition. The problem with this definition is that okay, this may not be an actual observation. What I mean by is the following. That's okay. Let me give you just one example of what I mean by this statement. Right? Suppose the data are as follows. Suppose you have two variables, X and Y. So suppose you have the following data on X, okay? And suppose you have the following data on y. Okay. According to this definition, the bivariate extreme value is right. You take the largest of the x's, which is 8, and you take the largest of the y's, which is 9. But this observation 8, 9 is not an actual observation, because the observations that you have on x and y are -5, 3, 0, 2, 1, 9, 8, 1, and 2, 3. There is no data where 8 and 9 are together, right? So this is an example where this is not an actual observation. Okay. Right. So that's one weakness of this definition. Nevertheless, this is the most common definition for a bivariate extreme value. Okay. All right. The next question is, you may remember when I talked about the univariate extreme values, we looked at the distribution of the bivariate extreme value after they have been scaled. So that's what I'm going to do now. So I'm going to look at the joint CDF of the following, right? I'm not just the Mn1 and Mn2, but a scaled version of Mn1 and Mn2. The reason for that was explained in the first chapter we did, because if you do not scale them, you will not get a meaningful limiting distribution, right? Right. So suppose suppose you have a random sample, x1, y1 up to xn, yn with joint CDF F. We want to find the joint distribution of the scale version of this and the scale version of this, right? Okay. You want to find this, right? And this can be written as the probability that Mn1 is less than or equal to Anx plus Bn, and Mn2 is less than or equal to Cny plus Dn. Right, and this can be written as, remember, Mn1 is the maximum of the x's, so this is the maximum of x1 to xn less than or equal to Anx plus Bn, and remember also that this is the maximum of the y's, so the maximum of the y's less than or equal to this. Okay. Now, if the maximum is less than or equal to a fixed number, then each random variable has to be less than or equal to this, right? So using that fact, we can write this statement as follows. Okay. And similarly, this statement can be written as follows. Okay. Now I'm going to combine this with this and so on until this with this. Okay, so I'm going to write this as the probability that x1 is less than or equal to Anx plus Bn, y1 is less than or equal to Cny plus Dn, right? Until xn less than or equal to Anx plus Bn, yn less than or equal to Cny plus Dn. Okay. Now we are told, if you go back to the beginning, we are assuming that these are independent and identically distributed, right? Which means that x1, y1 is independent of x2, y2, and so on until xn, yn, right? So hence, using independence in this step, we can write this as follows. All right. So this step, as I just said, this step here follows because of independence. Okay. All right. So we are not done yet. Okay. So in the next line, okay, I'm going to we are told that the joint CDF of x1 by 1 is capital F, and similarly the joint CDF of xn yn is capital F. So what you have here is equal to F. The first term is at F, capital F at an x plus bn, comma cn y plus dn. And the same thing until okay. So you have the same thing repeated n times, right? So what you have is the following. Okay, what you have is this. Now the question is, let me call this star. Okay, the question is the following. What is the limit of star as n approaches infinity? Now in the univariate case, I showed you that if the limit exists, then it must be of three types: the Gumbel type, the Frechet type, or the Weibel type, right? But in the bivariate case or the multivariate case, such a result no longer holds true, right? That is unfortunate. So let me say what happens in the bivariate case. If this is the following: if star approaches, say, a distribution function, a bivariate distribution function g of x comma y, as n approaches infinity for a non-degenerate, I hope you remember what this means, a non-degenerate CDF G. Non-degenerate, I'm sure you remember, it means that is something not useful. Like a degenerate CDF is something that takes the value 0 or 1, right? And a non-degenerate is the opposite of that, which is a CDF that can be practically applied, right? So if it approaches G of x comma y for a non-degenerate CDF of G, then possible forms for G can be uncountably infinite. All right, so this is the unfortunate result in the bivariate and the multivariate cases, that if a limit exists, that is, if this approaches G, then the possible forms for G can be uncountably infinite, right? Unlike in the univariate case, the possible forms can be only one of three, right? But that result is no longer the case in the bivariate or the multivariate cases, right? But fortunately, in the next video, I will explain a procedure to find G if it exists, right? So if the limit exists, It may not exist, right? If the limit exists, I will describe a procedure to find the formula for G, right? So that will be in the next video, guys.